Welcome to this video for Math 126-127. We're going to be taking notes on 2.3. So what we're looking at this section is we're looking at different polynomial functions and their graphs. And again, this is all review topics from your Algebra 2 course. But probably good things to get a reminder of. It might be helpful to just remember what the heck is a polynomial. So a polynomial is going to be an equation where we will have x to various powers, and each power of x needs to be a positive power. So it doesn't have to be 4 terms or 3 terms. We could have just 1 term. So like this is still a polynomial. And it doesn't matter at all about what the coefficients of those are. But, and it can be in ascending or descending order. But all of the powers here must be positive powers. So we're not going to have any powers that are going to be negative in here at all. And also with polynomial functions, those powers are all whole numbers. So just kind of keep that in mind when we're talking about a polynomial. So when we're looking at end behavior, what we're looking at is we are finding a way to describe, we're looking for a description of the heights that are being approached at the far left and far right sides of the graph. So usually when we're trying to talk about end behavior, there's some notation that's common for us to use. We might say something like this: as x approaches infinity, and then f of x would approach something right here. So what is this saying? This is saying as x approaches infinity, as we look at the far right side of the graph, f of x approaches what height? Now, sometimes it will approach a certain specific numerical height and kind of like start to turn towards the height. And then sometimes the function will grow without bound and maybe go up forever on that end or down forever on that end. So that's how we'll describe what's happening on the right-hand side. To describe what's happening on the left-hand side, we'll use this: as x approaches negative infinity, f of x or y or g or whatever approaches, again, some specific height. So this is describing the far left-hand side. And we would need to say what height the function overall has an overall trend or behavior towards on that far left side. So end behavior is only looking at the behaviors at the very extreme ends, the far right and the far left. It's not communicating any information about the function's behavior in the kind of intermediate, middle, interior portion of the graph. There's a test that we can use called a leading coefficient test that will allow us to know a little bit about behaviors of these functions by looking at the leading term. So what ends up happening is that when we're talking about the leading coefficient, we are talking about the coefficient or the number, the constant that is in front of the highest term. Now there are times that our polynomial could be written in descending order, but it doesn't have to be. So for example, let's say I had something like this: f of x is equal to 8x cubed minus 7x to the 4th plus 5. The leading coefficient here would be -7. That's the number in front of or multiplying the term with the highest power. And so what ends up happening is that the sign of the leading coefficient determines the behavior on the far right side. So this determines the behavior as x approaches infinity to the far right side. If that leading coefficient is positive, then f of x would approach positive infinity. And if it would be negative, it would approach negative infinity. This depends on the sign of that leading term. So the sign of the leading term, let's see, writing is hard. That just depends on the sign of the leading term or the leading coefficient. We call it the leading one because if we wrote this in descending order, this would be the one that would be written first. If it's not in descending order, you have to look a little more carefully. So let me kind of give you an example of this. I'm just going to use my graphing calculator here. So on this one, I did write this in descending order. So my leading coefficient is a positive 3. What this means is that when I graph this on the far right side, I should see that we're heading to positive infinity. And indeed we are. Here's my right side of the graph, and it's going up to positive infinity. If, on the other hand, I change this coefficient to a different sign, then I should be going down. In fact, we're going to explore this a little bit more in the light of this next portion because whether or not the highest function has an odd power or the highest term has a odd power or a negative power, whether this is an odd or negative or an odd or even, my goodness, degree, will tell us a little bit about the behavior of a function. So let's start with this one. We're going to look at an even highest power or an even degree with a positive leading coefficient. This matches the one that I just did. I have the highest power is an even number, and I have a positive leading coefficient. And so here's a picture of what this looks like. We're just going to really quickly record this. So this was y equals 3x to the fourth minus 7x squared plus 2. And it looked something like this. I think it was rather symmetrical, something like this. And so since the leading coefficient was positive, notice that we went up on the right-hand side. So as x approached positive infinity, y, in this case, I called it that instead of f of x, is going up to positive infinity. And if I look on the far left-hand side, that's true as well. So something that is true, when something has an even degree and a positive leading coefficient, we are going to approach positive infinity on both the right and left side. It doesn't actually matter what's happening in the middle. If I had a different function, I might have different behaviors in the middle, whatever's happening in here, but I'm still going to go up on the right-hand side because my leading coefficient is positive. And what will end up happening with the even degree is that the ends have the same behavior. And that will always be true with an even degree, is that what's happening on the right side and the left side will always be the same for those ends. So what this would mean is that if I'm looking at an even degree and I have a negative leading coefficient this time, so I change that, what should happen is I should be going down on both the right side and the left side. And again, we can have all sorts of different things happen in the middle. That doesn't matter. That will depend on the specific function, but we will go down on the right and down on the left regardless. So let's just take a look at a specific example. I'm going to go back to this equation. I'm going to just modify this slightly. I'm going to insert in here negative. And just because we're used to quadratics looking like W's, they don't have to, or quartics. I'm going to change this to a plus. Oops, not there. Right here. Just so that you kind of see the W shape. Sometimes having these kind of different signs here helps that happen. And we'll take a look. You might notice, again, on the right-hand side, we're going down, and on the left-hand side, we're going down on both of them. And that was because, so this one went like this. Something like that. That was y equals negative 3x to the fourth plus 7x squared plus 2. So for this one, as x approaches positive infinity, because we had a negative leading coefficient, that will determine the behavior on the right-hand side. Y will go to negative infinity. It'll go down. It'll match this sign right here. And because we have an even degree, the right side and the left side will match in their height, the type of behaviors they approach for the right and left side. Well, if even degrees mean they match, hopefully it makes sense that with odd degrees, the right and the left side have opposite behaviors. They will not match. So the right and left end behaviors will be different with any time that you have an odd degree. Okay, so kind of going back to the one that I had before, I'll just keep that negative power here. And I'm going to just change this to a power of 3. And let's just see what we end up with. And you might notice I had a negative leading coefficient. So on the right-hand side, we're going down. On the left-hand side, totally different behavior on the right and the left. This time the left-hand side is going up. So this one was y equals, I think we had negative 3x to the 4th plus 7x squared plus 2. So we went down on the right-hand side to match. So on the right-hand side, as x approaches positive infinity on the right, y went down to match the sign of the leading coefficient. And then on the left-hand side, as x approached negative infinity, we would have opposite behaviors and behaviors here. And again, you can have all sorts of things happen in the middle here. This one looks something like that. So if I just change this leading coefficient here on this one to a positive leading coefficient, this should go up on this side. And because it's an odd degree, the highest power, oops, well, hello, I am so sorry. We'll fix that. Was an odd number. The behavior should be different, so I should go down on the left-hand side. And again, what happens in the interior really depends from problem to problem. So let me just modify this. I'm going to just get rid of that negative. And again, you can see that we have that different end behavior. And so this looks something like this. And so on the right-hand side, as x approaches infinity, the right-hand side will match, positive or negative infinity will match the sign of the leading term, that leading coefficient. And then the left-hand side, since we have an odd degree, will always have different behavior than the right-hand side. So we're going to use this to determine the end behavior of the graph of each function. So what we have to think about is if we expanded this out, which I'm not going to actually expand this out, but if we expanded these expressions out so that they were polynomial expressions rather than being factored forms, what would the power be? And what would the sign of that highest power be? So what would the degree be? And what would the sign of that be? Well, right here, if I FOIL that out, the highest power of that portion would be an x squared times another x would be x cubed times x squared. I'm going to have x to the 5th as the highest power. And again, as I'm kind of foiling this all out, this would be a 1x squared times 1x times 2x squared. That would be a 2. And then we'd have other terms, which I actually don't care about them at all. So I have odd power, so the right and the left side should be different. I have a positive leading coefficient, so on the right-hand side I'll go up. And on the left-hand side, the behaviors are different. And whatever's happening in the middle, I don't care about. That's not what I'm asked about. And I don't really know a ton about that from what we've explored so far. So as x approaches positive infinity, y will match the sign of the leading coefficient. And then on the left-hand side, that behavior will be opposite and go down to negative infinity. Okay, so why don't you try part B yourself? I'll pause the video and we'll compare after you've had a chance. Just restart it once you're ready to take a look. So for this one, again, I'm really only interested in that term with the highest power. I would end up with next to the 4th times the next to the power of 3, 1x to the 4th, 1x to the power of 3. So that's 1x to the power of 7 times negative 6x to the fifth. And that would be a negative 7x to the fifth. And I'd end up with negative 7x to the power of 12 plus a whole bunch of other terms that I'm not actually concerned about. So because I have an even power, the right side and the left side will have the same behavior. And because I have a negative leading coefficient, the right side's going down. And that would mean the left side's also going down. And we have all sorts of stuff probably happening in the interior that I'm unconcerned about. So as x approaches positive infinity, g of x, that's the name of the output this time, will go down to negative infinity. So this is your far right behavior. And then if I look at the far left behavior, it will be the same. Now, something that you are allowed to do if you have an even power, since we know those behaviors will be the same, you could write it like this: as x approaches positive or negative infinity, the right side or the left side, the behaviors will be the same, and in this case, to negative infinity. So that's only allowed with that even highest degree, with an even degree. Otherwise, the behaviors will be different on the left and the right, and you cannot condense them like this. Okay, when we're talking about the zeros of a function, and we're really looking at polynomials here. Some other terms for zeros would be x-intercepts, factors, or roots. And when we're solving for the zeros, what you want to do is you want to set the output equal to 0 and solve for x. Now, there are many different strategies that we're not going to explore that are just not really in the context of this course for solving for higher powers, solving for x with polynomials with a degree that's higher than 2. You cannot use the quadratic formula here, by the way, unless you have found a way to kind of simplify out other factors. So the most common way that we will use is we'll use factoring for right now. There are some other ways using like long division, synthetic division that we are going to explore as well. So when we're looking at these, often they're written as factors. Like you can kind of look ahead to like number 3, you can see this one's already factored. And sometimes our factors show up with a higher power. They're repeated for those factors. What we call that is multiplicity. And so if a factor, which would then give you a 0, has a power higher than 1, so a power that is greater than 1, then that power is the multiplicity. It means that that factor, that answer, we only usually list that answer once, but we could say that answer is really showing up multiple times in the problem. So then that power is the multiplicity. Now, we've really mostly dealt in past years with problems that had a multiplicity of 1 for each factor. And we really didn't ever write out the multiplicity. So we're going to go ahead and do that for these next couple ones. The number 2, the problem is not yet factored. So let's start with that. Usually when I have 4 terms, I factor this by grouping, but I'm going to set the output equal to 0. And I'm going to factor by grouping, where I take a GCF out of the first 2 terms and then a different GCF out of the second 2 terms. So from the first 2 terms, I'll take out an x squared. Now, in factoring by grouping, if that third term has a negative, you always will need to take out a negative as part of the GCF. And now I can see, if I think of this as like the first half and the second half, each of these have a GCF with a factor of x plus 2. So I'll factor that x plus 2 out, leaving me with an x squared minus 4. And the x squared minus 4 could be factored as the difference of 2 perfect squares, as x plus 2 and x minus 2. A different way to write this could be x plus 2 quantity squared, since that factor shows up twice. So I really have 2 distinct zeros. I have x equals negative 2. Remember, when you have factors, they have different signs than the zeros. So watch for that. We're trying to find the value that would create a 0 for that factor. And then we do have some multiplicity. So for this first one, we have a multiplicity of 2. And for this one, we have a multiplicity of 1. Meaning we had a power of 2 for the factor x plus 2 that gave us the 0 of negative 2. And the other one only had a power of 1, only showed up one time. Let's take a look at this next one. This one's already factored, so we can get our zeros easier. Now remember, we don't have a 0 out front unless that GCF also had a variable with it. Otherwise, there's no 0 there. So I've got x equals negative 1/2, and that one has a multiplicity of 2 because we had a power of 2. And then I also have a 0 at x equals positive 5, and this one had a multiplicity of 3. And so that's what that means. You're really just looking for the power of that factor. A continuous function. A continuous function, what it essentially looks like is that we can trace along a function without lifting our pencil. Now we will later on this year this is like a description. This is not a definition. This is a description of a continuous function. And later on, we will end up with a definition, not for a while, not till we hit chapter 11 actually, for a continuous function. So we'll come back and get a better description of this. But a continuous function, again, we can trace along it. We never lift our pencil. So here's a couple examples. Here's a continuous function. Okay, I could trace that. I never lifted my pencil. Here's one that's not continuous. Maybe I've got something where there's a hole in the graph. Maybe it's a piecewise function. Or you might remember we did rational functions in Algebra 2, where we have these vertical asymptotes. And we had this spot here where I had to lift up my pencil in order to draw this. Same thing here. So we can have these different situations where we have this gap in a graph. Those ones are discontinuous or not continuous. Those last two with the yellow. Discontinuous. And this one is continuous. So all of the polynomial functions, again, we've got x as the base and our power is a positive number. All of those we're going to be continuous functions. There are other continuous functions out there like sine and cosine are continuous functions, for example. Tangent is not. We'll find out more about those later in the year. But really, we kind of have a little bit of information. Once we know something is continuous, we can make some conclusions. The first one comes from a really well-known theorem called the intermediate value theorem. It is totally okay for you to reference that as the IVT. That is a very universal abbreviation for this theorem. So if you, for example, go to college in Tennessee and you've referenced the IVT, which if you take calculus, you'll explore this theorem some more, everyone would understand what you're saying. So you can use that abbreviation if you like. Just to kind of get a little bit of information about the name, intermediate. Intermediate means between. Okay, so kind of as we look at this description of this theorem, a theorem is a statement that can be proven. This has been proven to be true. Look for betweenness to try to understand why it's called intermediate value. All right, so let's say we have a function f, and we have two conditions that we need to meet in order for the IVT to apply. The first is we need to be looking at a function that is continuous. Now, it doesn't have to be continuous everywhere, but it needs to be continuous on this closed interval from a to b. So from a to b, those are x values. Maybe a is here, and maybe b is here. They have to, we have to be able to trace along the function and not lift the pencil. Maybe something like this. And let's say, and by the way, this is kind of a special instance of the IVT. We'll explore the IVT without the second condition next year in calculus if you take it. But let's say that we know that f of a and f of b have opposite signs. So f of a would be the height of the function when a is the input, and f of b is the height of the function when b is the input. Well, then the conclusion that we can make, this is the conclusion, this is something that is true according to the IVT, is that there is going to be at least one value c, and I should probably put this in here, c is going to be inside the interval from a to b, so somewhere in between this, such that f of c is 0. Such a f of c is 0. Okay, let's break this down into maybe some more student-friendly language. Let's say that one endpoint is positive for its height and one endpoint has a negative height. And we know that this graph is continuous. It's smooth and connected. This connected graph. There are no gaps. That's what we mean by continuous. So we've got this connected graph. There's no graphs. If I have a positive value for one endpoint and a negative value for another endpoint, the only way that I could get from a positive to a negative without there being any gaps is I must cross a 0. And that is because 0 is going to be a height between a positive value and a negative value. This is why we call it the intermediate value theorem. Intermediate means between. This is saying if we know that one endpoint is positive, the other endpoint is negative, that we have to cross a 0 to change those signs, okay, if the graph is continuous. So, and then I've kind of restated that for you in typed. So here's how you could use it. We want to show that a continuous function g of x, and by the way, I knew that this is continuous even without that descripting word because it's a polynomial and all polynomial functions are continuous. If I went by that too fast, that's right there. Okay, we want to show that there's a real 0. We want to show that there is a height of 0 on this interval. Now, not every polynomial function has a real 0. They're all continuous. That doesn't mean they cross the x-axis, so we want to show that this one does. And we're not going to use a graphing calculator to do this. So here's what we can do. Let's evaluate g at -3. And really, all I really care about is g positive or negative when I use an input of -3. So this would be 3 times -3 cubed minus 10 times -3 plus 9. So this is -27 times 3 is -81 plus 30 plus 9. And I end up with some negative number. I end up with a negative. And if I look at g of -2, I end up with 3 times -2 cubed minus 10 times -2 plus 9. Make sure you always do powers first. This is -8 times 3 is -24 plus 20 and plus 9. Well, this time I get a positive. So, by the IVT, since g of x is continuous and g of -3 is negative. Now here's one way to say negative. And g of -2 is positive. Then g of x must equal 0 at least once on the interval from -3 to -2. So when it says to show it, part of that showing is to evaluate those endpoints. The rest of the showing is kind of a restatement of the IVT. I listed the name. I listed the conditions. I need to be continuous, and I need to have one endpoint of each sign. And then I can say, I guess I could add the word then in here, so there's a conclusion, that I will have a 0 on that interval. Now, I put at least once because that's kind of, at least one. Wow, because that's what the theorem actually says. it could actually happen more than once. We could cross that in between a whole bunch of times. There'd be nothing that says that we couldn't, but I will have to cross that 0 at least once. Okay, let's talk about graphing polynomial functions, and let's just assume that we're not using a graphing calculator in order to graph them. There's a couple things. We just want to find some key points to help us graph them. X-intercepts, again, what we want to do is we want to set the output equal to 0. And then we can factor to find x-intercepts. Y-intercepts, a y-intercept is going to be the value of the constant in the expression, but you could, if you wanted to actually do some work, we'll really be able to skip all of these steps, but you could set the input, or x, equal to 0 and solve for y. But really, truly, you're going to be able to see that. It's just the constant. It's the value of the constant. A constant is a number that does not have a variable. And then we can use end behavior as well to kind of sketch what's happening at the ends of this. And so when we're looking at the end behavior, one of the things that we can kind of do with here is just use that test that we were talking about on the previous page, that leading coefficient test. Then that'll help us see what the ends look like. Now, something that's true about x-intercepts is that the number of real and imaginary x-intercepts combined will always equal the degree of the polynomial. Now, the tricky thing is if some of them are imaginary, you're not going to physically see them on the graph, but you'll never have more real ones than your degree, and that's something that is kind of good to know. All right, so also we can have some symmetry in polynomial functions. I think we've talked about this just real briefly in chapter 1, but about the x-axis, even functions will have symmetry about the, I'm sorry, not the x-axis, around the y-axis. So you'll see this mirror image on the left side and on the right side. This is true if you have an even function, not an even degree. An even function, you might remember, that means you could plug in negative x into the expression, and when you simplify it, you get the same expression as the original. An odd function has symmetry about the origin. So if you kind of flip this around the origin, it does look kind of flipped here. You're going to be able to see that symmetry. That's true for an odd function. That's when if you substitute a negative x and simplify, you get the exact same expression as the original one, with every term having a different sign change. And then many of them have no symmetry at all. Most expressions have no symmetry at all. Okay, let's take a look at this one right here. Let's start with x-intercepts. To find x-intercepts, I'm going to solve this by factoring. So I'll plug in a 0, and I want to work on factoring this expression. Well, since I have this even power, what I can do is factor this in a very similar way to how I would a trinomial, but instead of x and x, in my factors, I'll have an x squared. And then I'm looking for factors of 1 that add up to -2. Only factors of 1 are 1 and 1. To get them to combine to a -2, they'd have to both be negative. And then if I continue factor them, these are both the difference of perfect squares. This is x plus 1 and x minus 1 for each of them. So I could think of this as x plus 1 quantity squared and x minus 1 quantity squared. My x-intercepts are the zeros, or the roots of those. Notice the sign change. They actually each have a multiplicity of 2. They didn't ask me to specify that, so I'm not going to take the time to. But that would be the 4 different zeros that we should have, since this is degree 4. All right, so there's a couple points on my graph. The y-intercept. The y-intercept is going to be the value of the constant. And what can end up happening is if you plug in a 0 for all of the x values, they all zero out, and the only thing that's left is the constant at the end that didn't have the variable. So the constant is my y-intercept at 1. And then my end behavior. My end behavior, this is an even power. So whatever's happening on the right should also happen on the left. If I want, I could kind of condense this. The right and the left behaviors will mirror each other in terms of their signs. They may not be perfectly symmetrical, but they will mirror each other. And then because my leading coefficient is a positive, these are both going to go to positive infinity. So on the right-hand side and the left-hand side, I'm going to go to positive infinity. Something that I think is helpful to understand with the multiplicity is what happens with the x-intercepts. If the multiplicity is an even multiplicity, what will happen, these both have the multiplicity of 2, is these bounce off the x-axis. They don't cross the x-axis. They bounce off of it. So what happens here is that this bounces. Same thing here. It bounces off instead of crossing it. Most of the time with an x-intercept, it crosses. Not true with a multiplicity that is even. Anytime you have an even multiplicity, this will happen. And so this should be going up on both sides according to my end behavior. This appears to have some symmetry. It looks to me like maybe this has symmetry like around the y-axis. Maybe this is an even function. Well, to determine that, I'm going to go ahead and replace x with a negative. Whoops, here we go. And simplify this. Well, that negative taken to an even power would go back to a positive. And so what ends up happening is that this is the same as the original function. This is an even function, which means this has symmetry about the y-axis. And you can see that from my sketch as well. My sketch is kind of sad, but I tried. So something that is worth us just kind of mentioning, if there is an even, if an x-intercept has an even multiplicity, then it will bounce off x-axis, bounce off the x-axis, and it will not cross it. Now, an odd multiplicity will cross the x-axis. So you'll have a chance to explore that more on your homework, and this is the end of the notes for 2.3.